Hi class, this is Neil, and this is part 2 of lesson 8. So in this part of the lesson, we're going to look at finding rates for growth and decay for various time units. So the key takeaway, especially from question 1 of the Do Now, is that the unit for the rates has to match the units of the exponents. And I'm just going to write this here. So for the examples we're going to look at, we're going to be given rates that are in terms of, for the first one in terms of years, and we're going to be asked to convert the equation to reflect a monthly growth rate and also a daily growth rate. So I didn't mention this in the first video, I did mention it in an email. You should either, if you can, print out this lesson, which is posted for you, or use some loose leaf paper or a notebook to kind of record what we're doing. All right, so let's look at example 1. So the revenue R of t of a small business can be represented by the function R of t equals 1,000 times 1 plus 0.021 raised to the power of t, where t is the time in years. All right, I'm just going to underline that. All right, so for part A, rewrite the original function in terms of a monthly growth rate. All right, so the first thing we have to realize is this rate that we're given, the 1 plus 0.021, is yearly. And we need this to reflect a monthly growth rate. So to do this, I'm going to draw a kind of a little graphic organizer for myself that lets me kind of keep track of what's happening. So here we have the rate, and we're taking that rate from years to months. So we're really going from a larger time unit to a smaller one. And one way to think about this is, what does 1 month represent in the terms of 1 year? Well, if 1 month passes, that's 1/12 of a year. So what we're going to do to recalculate our rate is take that 1.021 and raise that to the 1/12th power. All right, so to do that, we're going to need to get into Desmos or use some other calculator feature. So I'll go there now. I'll X out what I have. So that's going to be 1.021 raised to the power of 1 divided by 12. All right, and we do get a pretty lengthy decimal. And I'm going to record everything in that decimal up to the 8. So our new rate is 1.001733378. Again, pretty lengthy, but I'm going to record all of it. All right, so the other piece of the equation is the exponent. All right, so for my exponent, the t represented the time in years. So we're going from a t that represented years, and we want to change that into a monthly, an exponent that's going to represent the number of months. So let's say I was told that 2 years have passed. Well, that's 24 months. 3 years is 36 months. So really what I'm doing is taking the years, which is t, and multiplying it by 12. And that's going to be my exponent. All right, so to rewrite that whole equation then, I'm going to look at what we started with, which is here. And now I'm going to write that as R of t equals what we started with, so our starting amount doesn't change, that's 1,000. Our monthly growth rate is 1.001733,378, and that's going to be raised to the power of 12t. All right, so that's part A. Let's look at part B. You can pause the video if you want to write that down. All right, so for part B, we're asked to rewrite the original function in terms of a daily growth rate. All right, so again, I'm going to use my graphic organizer. So here we're taking a rate, the rate that we're originally given in our original problem is in years, and we're changing that to days. So what I kind of want to think about is, what does 1 day represent in terms of a year? It's 1/365th of a year. So I'll take my original rate, again from the original problem, which is 1.021. I'll raise it to the 1/365th power. All right, and we can do that in Desmos. All right, again, I get a little bit of a crazy looking decimal, and this one I'm going to record all the way up to the 9. All right, so that's my daily growth rate. Now for my exponent, so again, we're going from t years, and we want to change that into days. So if I wanted to figure out how many days were in 2 years, I would just multiply 365 by 2. So in this case, because we're using a variable, it'll be 365t. Okay, so my final equation for this problem, and I'm going to make a little space for myself just by erasing this little piece. All right, draw it again. All right, so my equation for part B is going to be R of t equals, and again, what I started with is 1,000. My daily rate is here, 1.0000569, and I'm raising that to the 365t power. All right, so that's for part B. All right, so take a minute, read the second example. Key questions that I have for you are, what is the rate given to us in? That is, what is the time frame that the rate is given to us in, and what are we changing to? So take a minute, read the problem, and we'll go through it in a minute. All right, so example 2. The population P of t of a regional animal population can be represented by the function P of t equals 14,000 times 1.02t, where t is the time in months. All right, so for part A, rewrite the original function in terms of a daily growth rate. So you should have said that here we are changing our rate from something that is monthly to something that is daily. All right, so to figure that exponent out, or what we're going to raise our rate to, there's really, for our purposes, always going to be 30 days in a month. So 1 day makes up 1/30th of a month. So I'll take that 1.02, I'll raise it to the 1/30th power. All right, again, you need to go to Desmos to calculate this, but when I do, I get 1.00066. So that's my daily growth rate. All right, so I also need to change here my exponent, because the exponent time units need to match the time units of the rate. All right, so here we're going from where t represents months to where t needs to now represent the days. So I'm just going to multiply 30 by the number of months, t. All right, so that gives me the information I need for my equation. So my new equation is going to be P of t equals what I start with, so 14,000 times 1.0006 raised to the power of 30t. Let me rewrite that 30t because it came out messy. All right, great. So let's look at part B now. All right, rewrite the original function in terms of an annual growth rate. So here, something a little bit different is happening. So again, I'm going to write my graphic organizer. So we have our rate, and our rate here now, we are going from months to years. So here we're actually getting bigger, or we're going to a bigger unit. So it's really going to be the opposite of what we've seen before. So if I know that 1 year has passed, really that is the equivalent of 12 months. Right? So notice it's really the opposite of what we did before. Instead of writing a fraction, when we're going bigger, we write the whole number. So let's recalculate our rate then. We're going to take what we started with, 1.02, we'll raise it to the 12th power. I'll need my calculator on Desmos to do this. When I use that, it's going to be 1.26824. Right, so that's my new yearly rate. And now for my exponent, I'm going from where t represented the number of months to now where t needs to represent, or that exponent needs to represent the number of years. So really what I'm going to do in this case is I'm going to take that number of months, t, and I'll just divide it by 12. And that's going to tell me the number of years that have passed. For example, if 24 months had passed, that's the equivalent of 2 years. All right, so now I have what I need to write my equation. So that's going to be P of t equals 14,000 times 1.26824 raised to the power of t. It changed to an eraser. So again, 14,000 times 1.26824 raised to the power of t divided by 12. Right, so that is now a equation that represents an annual growth rate. All right, take a minute to write that down if you need to. You can pause the video. And we have one more example in this section. All right, the value v of t of a car can be represented by the function v of t equals 30,000 times 0.95 raised to the power of t. And here we're told t is the time in years. Part A, rewrite the original function in terms of a daily growth rate. So with our rate here, we are changing from what? All right, you're right if you said we were changing from years to days. So we're getting smaller. Again, a day represents 1/365th of a year. All right, so I'm going to take my original rate, which is that 0.95. And I'll raise that to the 1/365th power. Again, you'll need your calculator to do that. Use Desmos, it really works. And when I recalculate my rate, it's 0.999859. All right, so let's go into our exponent. That's the other part of the equation. All right, so we're going from where t represented the years to where t needs to represent the days. So to do that, I would just multiply 365 by the number of years t. All right, so my new equation here, the equation that now reflects a daily growth rate, is going to be v of t equals 30,000 times 0.999859 raised to the power of 365t. All right, just one more example, that is. All right, so we kind of need to know certain time units here. Some problems may use words that might be unfamiliar to us, maybe not, right? So let's look at B. Rewrite the original function in terms of a decade growth unit, or decade growth rate. All right, so again, I'm going to make my graphic organizer so I can kind of see what's going on. So here we're going from years, and we're transferring that to decades. So to make even one decade, 10 years have to pass. So one thing to note here, like part B of example 2, we're going bigger. All right, so to recalculate my rate, I'm going to take 0.95 and I'll raise that to the 10th power. You got to get to your calculator to do that. When we do, we should get 0.59,873,69. All right, so for my exponent, so here, t originally represented the number of years. We're going into decades. So, what does 1 year represent in terms of a decade? Well, it represents really 1/10 of a decade. So I'm going to represent that with t over 10. So my final equation for a decade growth rate is going to be v of t equals 30,000 times 0.59,873,69 raised to the power of t over 10. All right, so that concludes really part 2 of lesson 8. There's a Google form assignment, and on that assignment for part 1, you're going to answer question 1 with an equation, 2 with an equation, 3 with an equation, 4 with an equation, and 5 with an answer choice. One thing to note when you do type your equation, so for this equation, when you do input that into the Google form, you're going to have to use a up arrow key to represent your decimal, or not your decimal, your exponent. So that's the key you would input to represent that you're using an exponent. All right, so I'll see you guys for the next part of this video.